So let's take a look at that one first. We were writing an insertion sort last time, just so this doesn't break us. So we'll come here, we'll just write it right after main here. So we'll say static int count vals. This guy will take a string as a parameter, and we're going to have a variable for counting. We'll start that guy off at 0. We're going to go through every single string, every single char in our string. So that's going to be our standard for loop. I equals 0, I is less than s dot length, I plus plus. Each time through, we want to ask if the current character we're looking at is a val. All right, so how do we do that? Well, we can give ourselves maybe a string up here, vals, and set this guy equal to A-E-I-O-U, A-E-I-O-U, if you wanted to do upper and lower. Then each time through, we want to know, is the character that we're looking for, or is the character we're currently looking at found somewhere in that string? So we can use index of to pull that off, right? So as long as index of gives us something other than -1, the guy we're looking at must be a val. So if vals dot index of s dot char at I is either not equal to -1 or is greater than -1, however you want to write it. Okay, so that means we're going to say count plus plus. So this guy says if the character we're currently looking at is found in the string called vals, increment count. In the end, we'll return count. That make sense? So something along those lines. If you didn't do the index of trick and you wanted to do the monolithic if statements, if it's equal to A, or if it's equal to E, or if it's equal to I, or if it's, you could have done that if that was the
Strings don't support buckets.
char at is the bucket. Is the rest of your logic right other than that? So it's a 0. If everything else is right and you just accessed the bucket of the string a little different, you'll get most of the points. Okay. Any other questions on that one? All right, so let's go ahead and finish writing insertion sort from last time. Oh, and just so I don't forget, the midterm will be the Thursday after break, so 9 days from today. Is that right? So it's Tuesday. We will talk about it in more detail on Tuesday, right after break. I'll kind of go through the slides and kind of point out the things that I think sound kind of important and the things that I think don't sound kind of important. So you sort of know what to expect, but just generally speaking, the exam will have 10 questions on it. Almost all my exams have 10 questions on them. It'll probably be half programming and then half kind of like a question like, what is this keyword? You know, stuff like that, where, you know, it's how an object refers to itself from within itself, or, you know, what's the difference between class methods and instance methods, those types of questions. So short answer essay. There won't be any true false, no multiple choice, just short answer essay and programming. Okay? So we'll talk about that in more detail on Tuesday, but that will be 9 days from today, the Thursday after break. And remember, in case you don't have it marked on your calendar, that the Wednesday after break is Reformation Day. I will probably be giving some extra credit opportunities if you go to some of those events. So I'll put those up on Slack. But I encourage you not to view it as just a day off. I encourage you to attend some of those Reformation events we have here on campus. Dr. Locklear is running one, and so they're kind of educational things, kind of connecting learning about the history of the Lutheran Church is one thing. That's interesting enough, I guess. But from my perspective, what's more interesting is, connecting a Christian worldview to just real life. And I think there's going to be several different things that will be interesting from that perspective. I think they sent the agenda out to CUW all, didn't they? Yeah. So you should all have what the agenda looks like. So if you want to kind of look at it, go ahead and do that. But I won't require you to go to a specific thing because I want you to go to what's interesting to you. But I'll have some sort of extra credit opportunity for attending some aspect of the event. Okay? So I want to strongly encourage you to do that. All right. So that being said, let's go to finish up our insertion sort from last time. And this is kind of a review from last semester. I think for the homework assignment, one thing we talked about last time is kind of the MacGyver solution to sorting. Like, look, if you didn't have an algorithm sitting in front of you, and that's kind of the situation we're dealing with here today, sometime in the past, all these different, most of the case, it's mathematicians, but regardless, some of the early programmers came up with, let's call it efficient algorithms for sorting stuff. All right. So insertion sort's one of them. We have shell sorts, we have merge sorts, all sorts of different sorts. Now, each one of these, what's the purpose of having a specific algorithm for sorting besides accuracy? If you have a bunch of data that you want to sort, last class we came up with an algorithm for doing it, right? We had a whole bunch of little helper functions, and we were finding the smallest value, then we were removing the smallest value, and all sorts of things like that. Now, would you call that a good algorithm? Or maybe would you say that was an impressive algorithm, or was it just an algorithm that worked? Probably more along the lines of that, right? It was an algorithm that worked. Now, is there anything wrong with that? Most of the time, when we're writing software, I say most of the time, 100% of the time, and a slow algorithm that works will beat a fast algorithm that doesn't work. Okay, so 100% of the time, that's going to be the better option. Now, every now and then we might bump into a problem where the speed of the algorithm is really, really, really important. And this is becoming less and less of the case as we move forward, because our computers keep getting faster and faster, right? Now, there are still problems that exist that fall into the category of time complexity problems. Did we look at the problem with adding fractions last semester? Did I talk about that one? It's actually an interesting one. In fact, we'll maybe write something with it today. So when you think about adding fractions, that seems to be an easy thing, right? If you would add 1/2 to 1/4, you got to get a common denominator, right? You multiply the two guys together, you get then you do the cross multiplying thing, you add them together, you get your new fraction. Well, then what do we like to do with fractions? We like to reduce fractions, right? So we like to get the fraction into its lowest common, into its the smallest representation. So 4/6 is actually 2/3, right? That kind of thing. So if I asked you to add together 10,000 fractions, and those fractions were of arbitrary size between, I don't know, maybe a numerator could be 1 all the way up to 999 million or something like that. Okay, big number, okay, but not infinite number. You would think off the top of your head that, adding those together, then reducing the fraction would be not that big of a deal. We probably would reduce after each addition. That way the fractions didn't get so large that they actually became too big for int or something like that. So forgetting about that as being a weakness, we don't think of that as being a horrifically complex problem, right? Just make sure you do the cross multiplication stuff, right? And how do you reduce a fraction? When I say 4/6, how do we reduce that? Yeah, you got to find the greatest common divisor of the 4 and the 6. So what do? You maybe pick between the 4 and the 6, which is the smaller, because you know it's not going to be bigger than that one, right? So maybe we start with the 4. We decide, are both of those numbers evenly divisible by 4? Nope, count down. Are both of those numbers evenly divisible by 3? Nope, count down. Are both of those numbers evenly divisible by 2? Yep, that's our answer. So 4 divided by 2 is 2. 6 divided by 2 is 3, 2/3. That's our final answer. Doesn't seem like hard math, right? What you would find is pretty quickly you could write a program that if you're adding, let's call it 1,000 numbers like that, it would take something like a week to run. Finding the greatest common divisor problem is actually a time complexity issue, because as the numerator and denominator get larger, you start with a pretty big number, and you have to count down by 1 until you finally find a number that evenly divides it. And sometimes you'll run into numbers that are not divisible, so the fraction is already in lowest common, is already reduced. So that act of reducing fractions, even though as a programmer we might perceive that isn't really a big deal, that should be a pretty straightforward problem, right? Is actually ends up being a time complexity problem, where if you don't write that in a more efficient way, your program will take a long, long time to run. We created this program, I think I remember maybe last year or the year before, and we left it running between classes, and it hadn't finished by the next, like if we left it running today, it wouldn't be done by Thursday. That's not what we usually expect with our programs today. It's a time complexity problem. So we actually have a known algorithm for calculating greatest common divisor. Anybody know what that is? The name of the algorithm is? It's actually something you might maybe learned in a math class. No, I'm talking about just an algorithm for determining what the greatest common divisor of two numbers is. If I give you two numbers and I ask you what is the greatest value that divides both of these guys, there's a kind of a popular algorithm that's... Huh? Oh, they talked about it in 150? Okay, and they usually, at some point they would talk about it in some math class. It's called the Euclidean Algorithm. Okay, the Euclidean Algorithm is an algorithm that it's not overly difficult, just some weird math tricky stuff, but we'll take, all you do is you change the way that you reduce those fractions, and you use the Euclidean algorithm for doing it, and that program that took 2 days to run before will take a fraction of a second to run. Same exact program, only changing the way you reduce the fractions. So there's an example where your original solution, while technically accurate, was not efficient, and we noticed. But that becomes less and less of a thing. That's one of those. That's an interesting one because at its heart, when you hear that problem, you wouldn't immediately assume that reducing fractions would be a big deal, right? Doesn't that feel like should be an easy problem? Our computers can do that super fast, no big deal. So it's a little bit deceiving, that particular problem, with the underlying idea of greatest common divisor of two numbers is the actual time complexity issue. Another similar but popular time complexity thing deals with finding prime numbers that divide into finding the largest prime number that divides into two relatively large prime numbers. So when you're dealing with prime numbers, that becomes so prime numbers are numbers that are only evenly divisible by themselves in one. Okay, so finding prime numbers that evenly divide into large prime numbers is considered to be prime numbers that evenly divide into large numbers is a hard problem. Because if it was a prime number, you wouldn't find other numbers that evenly divide them. But if you have two big numbers and you want to find primes that evenly divide into those big numbers, assuming they're not prime, that's a problem. Kind of similar to greatest common divisor, right? But the largest prime might not necessarily be the largest divisor, but it's, whatever. And actually, so that's a major time complexity problem, and it's what a lot of cryptography algorithms are based around. If you take the security class, Dr. Wall will talk about how a lot of our encryption algorithms, a lot of our security algorithms are dealing with this idea of prime numbers because they take a long time for us to work with them, right? But then that whole thing gets skewed as well. So, the idea is that what's a secure algorithm? Well, as long as it doesn't take a, let's say that somebody sends a message that you want to encrypt, and let's say the message is only good for a couple of days. So if somebody finds out what the message says in 6 weeks, that's not a big deal. I mean, it might be your preference that they wouldn't know that, but as long as they can't crack it by the time that the information is no longer important, we would consider that secure enough. Well, isn't that a moving target today? I mean, historically, we would have said, well, you have one computer, and how long would it take this one computer to guess the password for decrypting that code? Well, as our computers got faster and faster and faster, they can test more passwords, more keys in the same amount of time. So you had to keep increasing the size of your key. Well, now, what can we do? We can use distributed attacks. So instead of having one computer trying to guess the key, we could have a whole computer lab or a whole bunch of people all trying to attack it with their computers. So you could have 100,000 computers all working on that same problem. How do you stay ahead? So if you're the person trying to secure your data, how do you make your data secure when you don't know the nature of your attacker, the person who's trying to break it? If they're trying to break it on their laptop, well, you're probably going to be fairly secure with a medium security type of approach. But if you're trying to crack it with a fleet of computers, you might have a problem. So security becomes a kind of an interesting thing when it goes down that path. But swinging it back around, our punchline here is we do have some known algorithms for solving certain problems in an efficient way. And I'm sure we're going to keep coming up with algorithms for solving new problems. Every single day we're coming out with a better way of doing something. That's innovation, right? But not that often are we going to run into a problem where the algorithm is actually absolutely necessary. And why that's important for us is that means that as computer scientists, we don't necessarily need to sit here and commit all these algorithms to memory. We can find them somewhere, right? We can go find the algorithm on Wikipedia or something like that. But what we do need to be able to do is we do need to be able to take a set of instructions, which is what an algorithm is, and convert it into the equivalent code in whatever language we're working with. That's the programming skill set aspect of it. For most problems, we can come up with our own, solution to the problem like we did with sorting last time. All right, but as an exercise here, let's finish this insertion sort, then move on to the next thing we're going to look at here. So we were looking at an alternative sort to what we wrote in class last time. So looking at more of a traditional sorting algorithm, we looked at an insertion sort. So the very first thing we do is we take our string and we convert it to a character array, which allows it to be read and write, right? Because strings are read-only by default. So this allows us to move stuff around in the character array, and then we'll convert it back to a string in the end. Then what we always do is we start at position 1 in our elements and in our collection. And what we do is we take that position 1 and we say, how far forward, how far towards the beginning of this can I move it until he's in his the position he should be in, that I've moved him as far as he can move. Then we have this dude called the follower, because as we move somebody forward, we need to follow him to keep track of where we are, because we don't want to lose our next starting place. If I'm starting at bucket 1, after I've moved bucket 1 as far up as I can, I then need to move to bucket 2, then to bucket 3, then to bucket 4, so on and so forth. But as I'm moving bucket 4 towards the beginning, I don't want to break my remembering where my last starting place was. I need that follower to follow him back towards the beginning of the array to do my swaps until he's finally in the place where it's the most I can move him. Okay, so that's what these two variables are for. Now what we're interested in is whether or not we can, whether or not the value at position start pos, it'll end up being the position follower. So we're going to have follower start off at start pos. So we want to know if the guy that's currently at position follower should come before the guy after him. Or I'm sorry, the guy before him. Okay. Should I swap them? Now, before we can ask that question, though, we need to make sure we're not at bucket 0. Because if I'm at bucket 0, I'm already as far as I can go. All right. So while follower is not equal to 0, that effectively says I am not at the beginning of my list. That means I definitely have a dude that's before me. I might not be able to swap with him, but he definitely exists. So while follower is not equal to 0, and AR, which is my array, at position follower is less than AR at position follower minus 1. All right, so this says, it actually looks like I was doing this a little different, but that's okay. It's not going to be the end of the world. Whatever, it's fine. Actually, let me do it the way I was originally writing it, just so I probably already confused it, but let's just back off here. You saw me, I had a thing called pause in here. So I'm going to say, while start pause is less than AR.length. So what's this guy going to do? It's going to take start pause on a journey through every element in my array, bubbling it towards the top. Okay? Each time through here, I'm going to do that. At the end, I'll say start pause plus plus. Now, we could probably make an argument that this guy, because I know exactly how many times I'm going to go through, could be a for loop, right? I know that I'm going to go through length minus 1 number of times because we're starting start pause at 1. So I really could write this as for int. If I take start pause out of there, I could say for int start pause is equal to 1. Keep going as long as start pause is less than AR.length. Start pause plus plus. Now do some stuff. The very first thing I want to do in here is I want to set follower equal to start pause. That same reason we mentioned before. Because follower can change. We don't want to unnaturally modify start pause. All right, so the follower will start off at start pause. Then we'll ask the question. We want to move towards the beginning as far as we can. This is where that while loop comes in. So we're going to say while follower is not equal to 0, so while we're not at the beginning of the list, and AR at position follower is less than AR at position follower minus 1. While both of those conditions are true, what are we going to do? We're going to swap AR at position follower with AR at position follower minus 1, switch places for those guys, and then follower follows. So we'll subtract 1 from follower. We're going to need a temp variable for doing that. So we'll give ourselves a temporary variable. So we'll say temp is equal to AR at bucket follower. Then we'll say AR at bucket follower is equal to AR at bucket follower minus 1. And then AR at bucket follower minus 1 is equal to temp. Oh, this is a char array, sorry. We're swapping chars, not integers. So temp will be equal to the character at bucket follower. Then we'll replace bucket follower with whatever follower minus 1 is. So now follower minus 1 exists twice. Then we'll replace follower minus 1 with whatever we temporarily stored inside of temp. So that does the swap, and then follower follows. So we move towards the beginning of the array. So we do this over and over and over again until either follower is at bucket 0 or I should not swap. I don't have a smaller value before me. So when I'm done with this while loop here, I have moved the current value from start pause as far towards the beginning of the array as I possibly can. Now what do? I move to the next version of start pause and then reset follower to start pause. Do that over and over and over again. When all is said and done, I have a character array that should be sorted. So I need to go ahead and turn that guy back into a string. And we do have a constructor. So a couple different ways we can do this. If we didn't know that there was a constructor for the string class that took in a char array, then I could I write a little for loop that goes through and builds up a string, right? So we would say convert back to string. So we'd have for it I is equal to 0, I is less than, let me scroll up here, ar.length, I plus plus, and we're going to need a, so we'll say this dot, call it just s, what's our variable in here? Yeah, this dot s. So we'll say this dot s is equal to the empty string. We'll empty it out. Then we'll say this dot s is equal to this dot s concatenated with ar at bucket I. So that'll build up in s the contents of our array. So if we didn't know any better and we just need to convert a character array into a string, that's the code we might use to do that, right? Give us an empty string, loop through every bucket of the character array, concatenate each element onto the string. Now an alternative to this, so we can say this dot s is equal to new string ar. This will do the exact same thing. Okay, and the reason for that, if I go ahead and I bounce over to the documentation, and I go to the string class, even though up to this point we've used, I have shown the example because we were looking at the difference between a string literal and a building a string with the constructor using the new keyword. But we have these things called constructors that allow us to build objects. So the string class has a whole bunch of constructors. So we can use an empty constructor that just builds an empty string. We can build a string out of a byte array, bunch of other stuff, blah, 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 blah. We can build a string out of a character array. So this allocates a brand new string so that it represents a sequence of characters currently contained in the character array. So we do have a version of the constructor for the string class that I can hand a character array and it will build me a brand new string with the contents of that character array in it. Effectively, it does this. Now, is this that big of a deal? If we didn't know we could do that? No, not that big of a deal, right? Now, maybe when you were a brand new beginning programmer, this might have been a little daunting. But in general, is this something that, with just a couple of minutes of thought, we could all kind of work through at this point? We can turn an array into a string just using our concatenation stuff. So this is actually an important concept for us. And this really has to do with, it's actually something we've been talking about quite a bit in the department lately. I maybe mentioned it to you early in the semester. We have right before the semester starts, we have this thing called our faculty retreat, where we get together and they bring speakers in and they, are supposed to get us pumped up for the new year or whatever. But they talk about different trends that are happening in education and that kind of stuff. And something that I found fascinating from it and scary at the same time is something like less than 25% of, and this has been trending this way for a while, but this year, this is numbers from this year, so maybe last year it was similar or around the same number, whatever. Less than 25% of students coming out of high school are prepared for college. Isn't that scary? You spend all this time in high school, now you get dumped into college, and you're not ready.
I get that.
Huh?
There's a lot of people in my school who didn't meet any requirements that probably could have gotten them in college. But
Okay. No,
most of them did. Most
hold
of
on.
them
We'll let
did.
him in. This is a whole. Now we're dancing that line between colleges being a place for higher education versus colleges being a business.
Well, we have.
Yeah. You got a check that you can write tuition out of? Come on in. It's no problem. But then that devalues the rest of the thing.
You can get C's, low C's, and still get into the college that's in my hometown.
Yeah, so I mean, an issue here though is that grades aren't always the best measurement. You know, one thing that it's the measurement that society uses, right? And this is something I run into. Well, I've been teaching for a while, so this is 18 years. This is something I run into or have run into with specifically, at least from my experience, would be computer science students, and I assume it exists in other things too. But in computer science, we get a lot of some of our most talented people, have kind of a natural predisposition towards kind of programming, logic-y type stuff. They're good at that stuff. But all this other stuff bores them. Even though they're capable, they check out. They hopefully put enough effort to pass the English class, pass the psychology class, pass the sociology class. All these things they're not interested in. They always do well in computer science, but they got 1.2 GPAs because they fail everything else. I think that's a different problem. That maybe starts getting into discussion dealing with like gaming addictions and stuff like that. But in any case, it's an interesting thing that students are coming out of high schools less prepared, and it's been a trend. So and then that follows through to us. So when it comes, you get into college, what do? We have to lower the bar because, we got to keep our numbers up. We're a business. We got to cash checks and make sure you stay here for 4 years and all this stuff. And it's a sad scenario. But from our perspective, we got to look at why are you coming out of high school less prepared? Well, on one hand, we can look at some of the obvious things like, okay, I think real life starts earlier for people today, right? When I was in high school, school was your full-time job. Now it's completely common for people to have part-time or even full-time jobs when they're in high school. You're showing up to college with credit card debt and all this other stuff. That wasn't a thing years ago. So moving past that and just focusing on the technology side of things, though. You've grown up your whole life with Google, right? So even though would you say that you have access to more knowledge today than any group of people in history have had? Absolutely, right? So why do you have to store that much of it up here? So many of you have very strong skill sets in getting answers, right?
Just made us write code in a piece of paper.
Well, it's not even that. So this kind of becomes just a change in how we solve problems. We solve problems given the tools that are around us. And you have this great tool. You have Google. And if somebody asks you a question, Google it. It's fast. You get the answer quickly, right? But then what happens? So, if we just kind of dumb this down to the smallest thing, what ends up happening, kind of a trend I've seen, is we've stopped relying on our own critical thinking. Now, somewhere in the middle, there's kind of that where's the line in the sand? So what ends up happening is somebody asks you a question today, and rather than your go-to move being pondering it yourself for at least many questions, your go-to move is let's check Google. When you might have the answer there, or you might be able to figure the answer out or something like that. But because we become less and less reliant on our own critical thinking, even though we're capable of it, we just aren't used to using that tool because we have this convenient. Now we're carrying, Google in our pocket, so it's very convenient for us to always have the answers. You You want any sports score for the last zillion years? You can find it in Google in a heartbeat. Why memorize this crap? So there's this difference between getting the right answer and then also training our brains to solve problems. So one thing that we kind of, that where I see it just in this microcosm of computer programming is on little issues like this. I have a character array. I need it to become a string. How? What people will do is they'll start scouring the internet looking for that. They'll type into Google, convert character array to string, and they'll be reading through all these different things trying to find the answer. And it might not take very long to find that answer, but in general, that's your go-to move. Wouldn't it have just taken less time for you to consider it for a second, decide, well, do I remember that this is a thing? Whether you do or don't remember it, or whether you've never learned it, doesn't really matter. This is basic code, right? There's nothing, all of us know the parts of this code. This is something that we would accidentally memorize because it's just logic we write all the time. It's not very common for programmers today to just sit there and write their own version of this real quick, because why spend 15 minutes or 10 minutes or even 5 minutes looking for an answer when I can write this in 1 minute? And that is kind of, as I see it, just kind of this microcosm of maybe the issue. So we've stopped relying on our own mind. And I think we've all done it. I've done it. So even though I didn't grow up that way, now we become reliant on stuff. It doesn't matter how much we forgot. We can always look it up. We got reminders. I got a whole big list of reminders. I'm not going to remember to do it. I can't even go to the grocery store and make sure I come out with all the stuff I'm supposed to have. My wife gives me 3 things to get. Max I'm coming out with is 2. If I come out with 3, one of them is the wrong thing. So I have to have a list.
Even looking up something still requires a skill.
It absolutely does. No, it's not a stupidity thing. And I think that's the misunderstood aspect of this. In fact, we might say that the people today are more capable of getting answers to problems than any group of people have been in history. Okay? It does take a skill. Okay? We have a great skill at using Google. Some people are really good at getting answers. They can really put those queries in really, really well. But it is a skill. But what's happened is we've forgotten that we're actually smart problem solvers ourselves. We don't rely on ourselves, in my opinion, enough to solve problems. We don't take that breath. We don't say, okay, I was just asked the question, can I solve this on my own? If yes, is it worthwhile, or is the amount of time it's going to take me to solve it substantially more than if I just go out and get the answer? We're not taking that breath, is what it seems like to me. And then what ends up happening is we end up not being critical thinkers because we have this machine that thinks for us. And then we have this perception of being dumber, even though we're just not wasting our time doing something that we could do before. Make sense? So, when we come back to computer programming here, this is something that we should be able to just shoot from the hip on and not kind of freak out that, oh, I need to convert this character array back to a string. How? If it's not readily available, writing these couple of lines of code should not be a big deal. So that's something that I want you to start relying on yourself for. Over time, you'll add more tools to your toolbox, and you'll be able to, you'll come up with, oh, here's the easy way of doing it. Done. Make sense? So just something for you to consider, that when you're solving these problems, at least take that breath and ask yourself, can I do this myself? And for right now, if the answer is even borderline yes, I would encourage you to do it yourself, because that'll give you more practice solving problems. Even if in real practice, you probably shouldn't solve it yourself if there's already a good solution for it. Okay, so we'll convert it back to a string. You can do either of these 2 things. For all we know, under the hood here, it's doing this exact same thing. For all we know, it's the same. Okay? So we'll go ahead and we will set s equal to the string version of AR, of my character array, because we know how to build a string out of a character array. So now I have this insertion sort, which should sort a string. Come back in here. Right now I'm calling sort. So instead of, well, here, let's leave that in there for a second. So I'm going to run this right now, and we should see hello sorted. And this is not using our insertion sort. This is using our sort we wrote last time. Now I'm going to use our insertion sort instead of just sort. We get the same output. All right, so 2 different sorts. Certainly the one we wrote last time maybe makes more, at least it's the one easier for us to conceive as human beings. If I threw a bunch of, dice in front of you or something like that, or little chips that had numbers on them, that's kind of how we would do it, right? Find the smallest one, remove it from the list, put it here. Find the next smallest one, remove it from the list, put it here. That might be the way we go about it. So that's kind of the most human-like way of solving the problem, even though it's kind of a tedious solution. Insertion sort is a faster solution. Insertion sort isn't considered to be an incredibly fast sort, but it's a fast enough sort that maybe if it made a difference in a big thing of values that we would get similar stuff. Well, now, as a reminder, we talked about merge sort last semester. And merge sort relies on something called recursion, which we also talked about last semester. What is recursion? A recursion is when a function is implemented in terms of itself. Or maybe more simply, when a function calls itself from within itself. All right, so usually, just as I'm sure we did this last semester, the exact same thing, but we might think about the idea of factorial. So here's the factorial problem. So 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's how we calculate 5 factorial. Isn't it true that 5 factorial is equal to 5 times 4 factorial? 4 factorial is 4 times 3 times 2 times 1. And 4 factorial is actually equal to 4 times 3 factorial. 3 factorial is equal to 3 times 2 factorial. 2 factorial is equal to 2 times 1 factorial. And 1 factorial is equal to 1. That's our stopping case. Those are good pops. Do you know which joint you're popping there when you do that?
Something in my spine.
Just back pops.
Back pops,
You should Google it. Google it. It's called the sacroiliac joint.
Yeah.
SI joint. See? More you know. All right. So, this would be something that could be implemented recursively. Now, it could also be implemented iteratively. In fact, iteratively is probably the higher performance version of it because we can certainly count down from 5 to 1, right? We possess the power through a for loop. But if we're practicing recursion, we can come and write factorial recursively. We'll do this inside the driver thing. So let's write it iteratively and recursively just as some practice. So we'll say static int factorial it. And this guy's going to take in a number that we're calculating the factorial for as a starting point. And we'll go ahead and say int val is equal to n. So that's if n was 5, we'll start it off at 5. So then we're going to say for int I is equal to n minus 1. I is greater than 1, I minus minus. We could say greater than or equal to 1, but we know 1 times anything will be that anything. So we might as well just go up to something larger than 1. So if I passed in a 5 here, val would be equal to 5. Then we'll go from 4 down to 2, including 2. Each time through, we'll say val is equal to val times I. And then we'll return val. So that is the iterative version of factorial. Right? We're using a for loop. We're iteratively going through it and calculating this. This guy is not defined recursively. Factorial IT does not call itself in here. Make sense? Now, the equivalent, well, the functionally equivalent version, but the means to an end is different. Static int factorial recursive. We'll take an int n. We'll ask if n is equal to 1, return 1. Else return n times factorial rec of n minus 1. So that's the recursive version of factorial. If I'm looking at a 1, the factorial of 1 is 1. Otherwise, go ahead and return, for instance, if this was 4 factorial, return 4 times the factorial of 3. Does this make sense? So this is the recursive implementation of factorial. In this particular case, and if you wanted to make this look extra skinny, if you will, you might write it like that. That way the recursive version looks extra small, because one of the kind of the things about recursion is usually they have very short solutions, short elegant solutions, because the actual iteration is dealing with functions calling themselves. All right, and this goes back to that conversation we had that technically following an if statement, you do not need the opening and closing curly brace. It's one statement that you're allowed to have, and in this case, I only have one statement, so that's legal. But I would still say it would be better to write it like this from a clarity perspective. All right, questions about iterative versus recursive in practice? Now, for most of you, recursion is going to be a challenge for a while. It's difficult to kind of get your mind twisted into the recursive version of things. Once you get used to it, you actually will sometimes find recursion to be even easier than an iterative solution to stuff, because it just starts making sense. But typically, less experienced programmers struggle with wrapping their mind around recursion, okay, which is what makes merge sort so fun. All right, so when we go back and we talk about merge sort, so another algorithm for sorting, merge sort operates off of this fact of it's a divide and conquer. Yeah. This is divide and conquer algorithm. Who cares? We give names to different algorithms and stuff like that, but that's the type of algorithm it is divide and conquer. And it operates off this idea of a list is trivially sorted when it is a one list. So when I have one element, if I had an array with one thing in it, is it sorted by definition? I got nothing to compare it to, right? It's one thing, sorted. we're good. All right. So the idea is that we take our data, we keep splitting it up until we have sorted sublists. And once we have a sorted sublist, we bounce back up. We come off the previous recursive call. So now when we have two sorted sublists next to each other, so maybe I have something like maybe the list 1, 2, And then I have the, maybe the list, actually, let me write it a little differently here. Let's say this is the list 3, 7, and then I also have just the list 1. So I have 2 lists. I have a 2 list that has a 3 and a 7 in it, and then I have a 1 list that has a 1. Both of those lists are sorted within themselves, right? 3 and 7 are in order, and the 1 is in order. Okay? Don't worry about how the 3 and 7 got in order. We're actually mimicking that right now. So now what we do is we do this step called the merge step, where we start at the beginning of both of those lists and we start comparing them. So which is smaller, a 3 or a 1? A 1. So now we've burned past the end of this list. So now which is smaller, a 3 or an illegal position? 3. Which is smaller, a 7 or an illegal position? A 7. So we've merged those 2 lists together, and now we bounce up to the next guy. So this 1, 3, 7 becomes the left sublist of some other recursive call. So we keep dividing our lists in half and half and half until we get to one list, then we bounce up, and then we sort that little tiny list. Then we bounce up again, and we sort this slightly larger list. Then we bounce up again, we sort this even larger list, each time using that merge step. That make sense? Remember this from last semester? Okay, so let's go ahead and write this guy. So we'll do this inside of our superstring. So we're going to have another kind of sort. Public void merge sort. Okay, and merge sort is going to sort our list. So very first thing we're going to do is we're going to go ahead and get our array. So char array AR is equal to this dot to char array. We wrote our own version of that. We could also say this dot s dot to char array, since we happen to know that strings also have a way of converting themselves to char arrays. But this is our version of to char array, which converts that guy to a character array. Okay, so now for merge sort, we're going to ask ourselves, is this the 1 list? If my string only had 1 element in it, it's already sorted, right? So I'm only going to do anything in here if AR.length is greater than 1. All right, so only if it's greater than 1 am I going to do anything. And what am I going to do? I'm going to go ahead and I'm going to call my merge sort helper. And this guy takes in an integer array. So I'm going to have another little function that'll going to help me make my recursive calls here. Okay, so my merge sort helper will take in an integer array. So, char array, thank you. Usually I'm sorting integers when I teach merge sort. This guy's going to take in a char array. So, very first thing I'll do for merge sort, I'll say, go ahead. And I'm actually going to have 2 other things. I'm going to have an int begin and an int end to get passed in here. All right, this keeps track of what portion of the array am I currently focused on. All right, and we'll have begin be the first position in the array, and then that we're focused on, and we'll have end be the last position, the actual location of that last position, not one past it. So you know how like the length of an array is actually not a legal position. Length minus 1 is the last legal position. We're going to have end be an actual legal position in our array. So that means when I call merge sort helper for the first time, I'm going to say this dot merge sort helper, passing it AR, passing it 0, and passing it AR.length minus 1. The the beginning of my array and the last legal position in the array. That's what I'm calling merge sort helper on. This is effectively my merge sort algorithm right here. I just needed a helper thing because I'm going to need a function that can take a beginning and an end. And we don't want to really make our person who's using our merge sort have to call it with all this extra crap in there. All right, so what did we say? Merge sort helper's job is to go ahead and get the portion of the list. So if we want to get a little comment here, this guy's job is to sort in place the portion of the array from begin to end. Okay, sort in place means I'm actually going to move things around in memory so that the actual pointer to the array has those elements rearranged. Notice that this guy does not return a value because we are manipulating the actual location where that array is and moving stuff around. Okay, so that's what I mean about sort in place. Okay, so we are only done. We don't have to, well, my job here is to sort in place. The only time that I have to do no work is when begin and end are the same, right? If begin and end are the same value, that means it's the one list, which means it's already sorted, which means I don't have to do anything. So if begin is not equal to end,
If you ask that earlier,
forget this guy even exists. This guy's just he's a wrapper so that our person out here who calls it, when we call merge sort up here, we're eventually going to call merge sort, we don't have to pass extra crap in here. We don't have to pass a begin and end. That would be like inconvenient to use,
yeah,
right?
but you put the next statement,
No, I know, but if I'm using this tool, if I'm the programmer, I would have to put in a 0 and a 7 or something like that there, which kind of is like a different, you're making them solve a problem that they don't have to solve. Yeah. So instead, we're going to go ahead and build into our merge sort. This guy does that little thinking for us. And he comes up with the correct begin and end. So this is actually our merge sort. So you can just pretend like this is the original call. Everybody understand that? Yeah, this is just the convenience for our users so they don't have to kind of know about the existence of that begin and end thing because it's important for the algorithm, but not important for the person calling this. They just want to sort it. So they call merge sort and just let the magic happen. All right, so if begin is not equal to end, okay? Or we might ask the question, maybe even the more correct way of saying it, as long as end is greater than begin. Ultimately, they'll mean the same thing to us, right? So as long as end is a bigger value than begin, that means we at least have a 2 list. Otherwise, so this is really asking, is this bigger than a 1 list? So if end is greater than begin, it's bigger than a 1 list, I have to do stuff. All right, now what stuff do I need to do? Well, since I only know how to trivially sort 1 lists, if I'm in here, I don't have a 1 list. So I need to go ahead and make sure that I handle the 1 list thing. So I need to go ahead and divide my list up. So I'm going to divide my list in half. So I'm going to keep track of an int b1, int e1, int b2, int e2. So that'll be the beginning and end of the first half of the list and the beginning and end of the second half of the list. So b1 is going to be equal to begin. e2 will be equal to end. These guys in the middle here, this is where we need to do a little bit of magic for calculating where's the end of our first half and where's the end of our second half. So sometimes what we'll do is we'll say something like we might say n divided by 2, for example. And we might think that's like half the list. But the reality is that will work when we're dealing with the left half. But if we're dealing with the right half of the list, we'll have crossover. It's going to take us back the other direction. So what we actually want to say here is we want to say, what's it, n plus begin divided by 2. So our first end will be n plus begin divided by 2. And our second begin will be E1 plus 1. That make sense? That will divide our stuff in half. So for merge sort, this guy right here is usually where people screw up, calculating where that midpoint is. Okay, so once I have that, I know that I can call merge sort helper on the first half and call merge sort helper on the second half. So I'll call merge sort helper on the same array, but passing it B1 and E1. And I'll call merge sort helper on the same array, passing it B2 and E2. So I'm making 2 calls to merge sort helper. When I get to this point here, we know that the array from B1 to E1 is sorted. We know that the array from B2 to E2 is sorted. We must merge them together. Make sense? So this is kind of where the magic comes in. Because we ask ourselves, well, how do we know that B1 to E1 is sorted and B2 to E2 is sorted? We haven't actually done any sorting, have we? We actually have done some sorting. What sorting have I done? Trivial sort. So we bounce off the backboard when we get to 2-1 lists, right? That's when we bounce back up and then we sort those guys. So now this is our merge step. So we're going to go ahead and create a char array called temp. And this guy is going to be big enough to hold the number of characters we're dealing with here, which is all the characters from begin to end. All right, so if begin was 0 and end was 7, that's 0, 1, 2, 3, 4, 5, 6, 7. That's 8 characters, right? So is it end minus begin plus 1? Is that my size? This is going to be a new char array, end minus begin plus 1. That'll be the size of my temporary array.
And we're sure that won't be end minus begin plus 1.
Minus begin plus 1.
So like...
No, because this is just going to be a size. We're going to put it back into the right place later. Yeah, this just needs to be a little container to throw some stuff.
I'm saying order of operations, it's definitely going to take end.
Yeah, it'll be left to right for minus and plus. Correct.
Right.
Yep. Okay, so where we'll leave off here, we'll say perform merge step. All right, then I'll go ahead and introduce an error. So we'll know for next time. All right, so no homework over break. I will see everybody on Tuesday. If you're traveling, travel safe. Also, go ahead and take a look at the schedule for next Wednesday and kind of plan on attending something with that. And I'll put out the information for how the extra credit will work. Also, a reminder, today's faculty, student, staff Bible study. God and Grub, you get free lunch, go to the cafeteria, you sign in, then grab a tray, go and eat your lunch, then take it down to the terrace room by noon is when the Bible study actually starts.